Hello class, we're about to start section 2.3, Venn diagrams and set operations. Our objectives: understand the meaning of a universal set, understand the basic ideas of a Venn diagram, use Venn diagrams to visualize relationships between two sets, find the complement of a set, find the intersection of two sets, find the union of two sets, perform operations with sets, determine sets involving set operations from a Venn diagram. Understand the meaning of and or. Use the formula for N of A union B. Universal sets and Venn diagrams. The universal set symbolized by union is a set that contains all elements being considered in the problem. We normally use a square or rectangle to represent the universal set. Subsets within the universal set are depicted by circles, or sometimes ovals or other shapes. The diagram to the left is called a Venn diagram. A Venn diagram gives us a visual display of the relationship between sets. It is named for John Venn. Example: you are doing a study on women aged 18 to 49 and their smoking habits. The universal set for your particular problem would be all the women aged 18 to 49 that you interviewed. To represent subsets of the universal set within a Venn diagram, we normally use circles that are within the rectangle. Continuing our previous example, let's say you ask the women in your survey whether or not they have ever smoked. Some will say yes and some will say no. Specifically, you are interested in the ones who do smoke. You can represent the set of 18 to 49-year-old women who smoke in your survey as: the women who smoke is represented by the set A in the Venn diagram. Also notice that the circle A is totally within U, indicating that A is a subset of U. The region inside the rectangle and inside the circle A are those women who smoke. The region inside U but outside A are those women who never smoke. Representing two sets in a Venn diagram. There are various ways to represent two subsets of a universal set in a Venn diagram. Let's use the following example to illustrate these different representations. Example: now let's say you decide to ask a second question about the women's drinking habits. Specifically, you ask, do you drink alcohol? Those surveyed either say yes or no. Now a second circle will be introduced into our Venn diagram. Specifically, we would denote B as those surveyed who do consume alcohol. Now we have two overlapping circles in the diagram. Let's analyze what each of the four regions of the diagram represent. Region 1. These are women aged 18 to 49 that smoke but don't drink. Okay, as you see here, there's no overlap with Region 1. Region 2. These are women aged 18 to 49 that smoke and drink, which is this population here. Region 3. These are women aged 18 to 49 that drink but don't smoke, which is this region here. Region 4. These are women aged 18 to 49 that neither drink nor smoke, which we notice is here. In this particular example, we assume there is overlap between the smokers and drinkers in our survey. However, sometimes sets can be disjoint. Relationship 1. Disjoint sets. Definition: two disjoint sets are those that do not overlap and hence have no common elements. We will use a diagram like that to the left if we discover no one both smoked and drank. Relationship 2. Proper subsets. Sometimes sets are proper subsets of one another. Recall the definition of a proper subset. If A is a proper subset of B, all the elements of set A are elements of set B. A is a proper subset of B. We represent this case on a Venn diagram as, in this particular diagram, notice that set A is completely within set B. For our example, that would mean all the women who said they smoke also said they drank. However, the region outside of A and still within B would be those women who said they drank but did not smoke. Sometimes sets are equal. For example, if we found out that all the women who smoke also drink, and vice versa, our two sets would be exactly equal. We represent this on a Venn diagram as shown in the diagram to the left. If you notice here, there's only one circle here. That is because they have all the same elements, and we will put that A is equal to B. Set A is equal to set B. Now we come to relationship 4, sets with some common elements. In math, the word some means there exists at least one. If set A and set B have at least one element in common, then the circles representing the sets must overlap, as shown here with region 2. This is illustrated in the Venn diagram to the left. In region 2, the circles overlap. This is the region that represents at least one woman that both smoke and drink. Examples. Describe a universal set that includes all the elements in sets A and B. We have A is horses, cows, and pigs, and B, which is goats and sheep. A possible universal set is farm animals. Then we go to example 2. Describe a universal set that includes all the elements in sets C and D. C is equal to rose, petunias, lilacs. D is tulips and daisies. A possible universal set is flowering plants. Now let's take a look here. Now first of all, in set A we have horses, cows, pigs, and then in set B we have goats and sheep. We notice that none of these elements are the same. So what we could do is this: we could draw our box here. And again, it says a possible universal set is farm animals. So we could put an F here to denote that this region here is farm animals. Now we would do one circle here, one circle here. For our Venn diagrams, we would make this A and we would make this B. There is no overlap. So this is basically our Venn diagram. I would like to make one little change here. Instead of us using F to represent the universal set, let's stay uniform and we could use the U like we did in all the other sets, and that will represent the universal set. Okay, now we come down here to number 2. It says describe a universal set that includes all the elements in sets C and D. Now we have roses, petunias, lilacs, tulips, and daisies. None of these match up. So we would draw our box here. Now, of course, it's not the best looking, but you get the idea. And we would draw our Venn diagrams. We have C and we have D. Now if you notice, in both of these representations, both of these are disjoint because none of the elements overlap. Now it says here, find the complement of a set. The region outside the circle but inside the rectangle represents the elements that are in the universal set but not in A. The elements in a universal set that are not in A are called the complement of A, also written as a complement. This idea can be expressed in set builder notation as follows. The complement of A is basically that X is part of the universal set, but X is not part of A. The complement of set A symbolizes by A complement is a set all units in the universal set, but not an A. Example, we have the universal set of 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have set A, which is 1, 3, 4, 7. It says find A complement. So what we would do is A complement would be all these other numbers that are not an A. So we would have 2, 5, 6, 8, and 9. That would be our A complement. Now, we have the intersection of sets. The intersection of two sets is the set of elements that the two sets have in common. We have A intersect B means the elements that A and B have in common. When you see the intersection symbol, think AND. The intersection of sets A and B written A intersect B is a set of elements common to both set A and set B. The intersection of sets A and B can be expressed in set builder notation as follows. A intersect B means that X is in A and X is also in B. That means X is contained in both of these. So now we have example. If A is equal to 1, 2, 3, 4, 5, and B is equal to 2, 4, 6, 8, then A intersect B is equal to 2, 4. Now we look here. We had 2 and 4, and they have nothing else in common. So A intersect B is 2, 4. Now we come to our next example. If A is equal to 1, 2, 3, 4, 5, and C is equal to 1, 3, 5, 7, 9, find A intersect C. So we know A intersects C. We look at all the elements they have in common. They have 1 in common, they have 3 in common, and they have 5 in common. So this set would be 1, 3, and 5. And that would be your A intersects C. Now we come down here to our next example. We have A, B, C, D, E intersect C, D, E, F, G. Now we look at what they have in common. They only have in common C, D, and E. So the intersection would be C, D, and E. Now example, we have 1, 2, 3. We have the ellipse 24, 25 intersect 3, 6, 9. The ellipse 30 and 33. Now we remember we must recognize what this ellipse means here. We have 1, 2, 3. That means that this is going in sets of 1. They're increasing by 1. So this will go 4, 5, 6 all the way up to 24. Well, actually up to 23, then 24. Now this is going by 3s, 3, 6, 9. So then we will have 12, 15, 18, 21, and then 24, and so on. But the numbers that we're looking at is this here. We're looking at this ellipse. Well, actually, we're looking at this set and see what they have in common. Now, if you notice, we have 3 in common. We have 3 in common. Now, we know in this ellipse, there's a 6, and there's also a 9 in that ellipse. So we have 6 and 9 in common. We know also there's a 12, a 15, an 18, and also a 21, all contained in this ellipse. So we will have 3, 6, 9, 12, 15, 18, and 21 all in common. Well, actually, we will also have 24. And this would be all in common. So our answer here would be, we will have 3, 6, 9, 12, 15, 18, 21, and also 24. So this right here would be the final answer. Now we have our next example. We have PQRS intersect the node set. Now we know every set has a node set, so the only thing they have in common here is the node set. So our final answer here for this example would be the nose